So I developed a set of libraries, and MOAB is one of those libraries, and that's the library for handling mesh. But also when you're dealing with mesh, oftentimes you're not dealing with mesh alone, but also geometric models. And if you're doing fancy things like adaptive mesh refinement, you're handling geometric models in the mesh at the same time. And so there are other libraries for handling those things that I'll mention just a little bit about, but not a whole lot. So the slides have a little bit more information. And then I'll talk about some of the tools that come with MOAB in particular. Okay, so Lori had a little bit of information of this type on her presentation earlier. In PDE-based simulation, you're discretizing PDEs over a discrete representation of a spatial and possibly a time domain. And then you're solving for specific discrete models, like you're taking your PDE and discretizing and solving that. What that looks like is you have a description of the continuous domain, which is often a geometric model. You discretize that into some type of mesh, and you generate results on that using finite element analysis or some other discretization type. Sometimes the details of these geometric models matter, and other times they don't. So generating the mesh sometimes isn't a straightforward thing because oftentimes you have to go clean up the geometric model or take details out. I usually say that if you're doing massively parallel processing, generating meshes that are very large and very finely resolved, you usually want to resolve the geometric details on that same degree of resolution, but really it depends on what kind of analysis you're doing. Depending on the geometric features and what sort of analysis you're doing, sometimes generating the mesh can be trivial. Like I love working with climate people because I think I can generate a mesh for the sphere. But other times, like in reactor analysis, even in 2D, the model can be fairly complicated. In 3D, it can get just insanely complicated. So sometimes meshing is a problem, other times not. This is a mesh guy talking, but mesh and data on the mesh are involved in the simulation at the front end in mesh generation during the analysis, because that's what the analysis uses to get an idea of the discrete model. And they're also relevant on the back end because that's the basis for visualization and data analysis. So when you're dealing with a mesh, you're kind of touching the whole scope of the simulation process. That tends to make us a jack of all trades. It also tends to make us meshing people the people that get blamed when anything goes wrong. And sometimes that blame is valid because oftentimes when you're dealing with the mesh, you often tend to drop data along that simulation process, either before or after. A lot of the problems in going through the simulation process and iterating it have to do with dropping data along the way somewhere. Okay, so my primary purpose here today is to describe mesh in the context of the mesh library that I developed, which is named MOAB. And here's kind of my one-slide description of that. So MOAB's a library for representing and manipulating structured and unstructured mesh models. It supports various entity types of a mesh, so your standard finite element zoo, vertices, triangles, quadrilaterals, and other kinds of elements. Polygons and polyhedra, which are relevant sometimes in finite volume analysis and others, and structured mesh, which Rob just talked about. MOAB's implemented in C++, but it uses an array-based storage model underneath, and that can be important in terms of memory usage and sometimes even in terms of execution time. It provides I/O from and to various formats. If you've dealt with any of the Viz tools, you know that they each come with about 80 or 90 mesh formats that they read and they write. MOAB doesn't provide quite so many, but a lot of the mesh formats that you'll see mesh and data coming with are supported by MOAB directly. When you're using MOAB, you'll deal mainly with three parts: the core representation, the tool classes that provide higher level functionality that you access programmatically, and then tools that are packaged and compiled with MOAB that use the library to do various things that you'll use from the command line. MOAB's parallel model I'll talk about in a minute, and MOAB's been run on 32,000 cores and more. So we've run some pretty large meshes on some fairly large core counts. So just some general terms when you're dealing with a parallel mesh model. First of all, we talk in terms of the kind of partition that you'll be dealing with. Most often people tend to deal with element-based partitions, where each element of the mesh, or the highest dimensional entity in the mesh, is assigned to exactly one processor. Elements assigned to a given processor are called a part. We'll also talk about shared entities, and that's an entity that has a representation or is used in multiple parts. So that's often entities on the boundary between parts. So in this case, a 2D mesh, the vertices and also in some cases the edges will be shared between those parts. Part interfaces are entities that are used in multiple parts. We also talk about ownership of entities. So each mesh entity is owned by exactly one processor, even though it may be represented on multiple processors. And we also talk about ghost entities where you have a shared non-owned entity. So say this triangle here, that's explicitly represented over on this processor because it needs neighbor information from the neighboring mesh. So in terms of a distributed memory parallel computing model, even though this entity is in a different part, the code or the solver that's solving physics on this triangle may need to reference variables from the mesh next to it. And so we exchange ghost entities to accomplish that. And those are also sometimes called halo entities. The degree of parallelness, that's my word, that an application has depends on the application requirements. And for MOAB, you can adjust that dynamically during the run. So for example, in some cases, every processor needs the entire mesh. And there are some applications which run like that. That limits the size of mesh you can run, but in some cases that's useful. Other times you have a domain decomposed mesh, like an element-based decomposition. Oftentimes you need shared vertices, and sometimes shared non-vertices like shared edges to be resolved between processors. Rob referred to that. In that code, I think you have to explicitly tell it what the shared vertices are between parts. And in some cases also you need one or more layer of ghost elements to be exchanged. Now in MOAB you can tell the code to do that for you, so it'll take care of resolving that sharing. So you don't need to be involved in that. Okay, so MOAB's parallel mesh model is based mostly on an element-based partition where each element is assigned to exactly one part. It supports an arbitrary number of layers of ghost elements, and I'll get to some code that shows how you do that programmatically in a few minutes. It also supports various parallel mesh constructs. For each entity that's shared between processors, one of the fundamental assumptions in MOAB, or one of the things that we maintain, is that if an entity is shared on any other processor, you always know what those other processors are and what the handle of that entity is on all the sharing processors. So for any entity that exists on other processors, you can always tell how to address it on that other processor. And that's important for things like exchanging variables on those mesh entities. So the sharing data is stored as either a single integer or handle in the case where an entity is shared with a single other processor, or it's shared as a list of processors and handles in the case where an entity is shared with multiple other processors. And distinguishing between those two saves a little bit of memory. So the parallel model or a parallel mesh is usually initialized by reading a file and just telling the system, okay, read this mesh from this file. The file usually contains some decomposition in it telling which elements go to which processors. The one kind of decomposition that people work with most of the time is one that's explicitly generated by a tool like Zoltan or Metis. And that actually uses some method for optimizing the load balance and the communication between processors. But that's not the only kind of decomposition that could be used to load a mesh in parallel. And sometimes meshes come with that with a decomposition that you can use as that parallel decomposition, like material settings or geometric volumes. So MOAB can use a number of different partitions that already exist in the mesh. MOAB does single parallel read and write based on the parallel HDF5 library. The parallel functionality is usually accessed through the parallel com class in MOAB. And so in general, the parallel model for MOAB is that locally each instance of the library looks like a local mesh, and any parallel characteristics of it you can think of as annotations on the mesh. So you can get all the vertices in your local mesh and say, okay, now which one of these are which ones of these are shared with other processors, and ParallelCom provides functions for querying that kind of parallel data. Oftentimes when you're working with libraries, you need to know what's the data model that this library exposes. And think of the data model as kind of the language that's used to interact with the library and to find out information about it and pass data through the interface. MOAB uses 4 basic types of data. Entities, and those are the entities in the finite element zoo, like the vertices and the triangles and so on. Entity sets, which are simply arbitrary collections of entities and other sets. In our case, entity sets have parent and child links with other sets, and those links are distinct from contains relations with other sets, and that allows you to embed a graph of sets into the mesh model, which is useful for a number of different kinds of data that often comes with meshes. You access MOAB through an interface object, and think in terms of object-oriented programming. That's the object through which you call functions. And then tags, which are an annotation of data on entities, entity sets, or on the interface itself. These tags are used for both fine-grained and coarse-grained data. So an example of fine-grained data would be a variable that you put on vertices, so a vertex-based temperature, for instance. An example of coarse-grained data would be something like the provenance of a mesh. So you have an entity set, and a tag on the entity set tells which file it was read from or when it was generated or something like that. In practice, these sets and tags are used for a variety of mesh groupings that often come with the mesh. So for instance, you can phrase a parallel partition as a set of sets where each set represents a part in the mesh, and a tag tells it that this set is a part in a parallel partition. You can use it for vertex-based variables. If you're familiar with CAD-based mesh generation, you can even use these sets and tags and the parent-child links between sets to embed the geometric topology of the geometric model that was used to generate that mesh. And in the case of applications like adaptive mesh refinement, that kind of information is critical for recovering kinds of metadata that come with the mesh. I'm not going to spend too much time on MOAB internals, but this is a picture of it. A couple important things here. In MOAB, an entity handle is what you use to refer to a mesh entity, an entity set, or the interface itself. Think of an entity, in the case of mesh entities, think of a handle as with some other library, you might get a pointer to a node or a pointer to a face. So an entity handle is sort of like that, except that it's not really a pointer. In MOAB, the type of an entity is embedded in the handle as the top 4 bits. And that stores whether it's a vertex or a triangle or a quad or so on. And the remaining 28 or 60 bits store a sequential ID for entities. Now this is an integral data type. Oftentimes when you're dealing with mesh, you create mesh in groups. And so if you create like 1 million vertices, you'll get 1 million handles back, but you don't necessarily need to store 1 million handles to know that you have those vertices, because when you allocate them as a block in MOAB, you allocate handle number 1 first and handle 1 million in 1 million. So we also support a range data structure, and this is a class for storing subranges of contiguous entity handles. And in practice, since you often have high degrees of contiguity in the handle space with entities created in MOAB, ranges provide near constant size storage for storing large lists of entities. That's useful for both memory and also for time efficiency, because ranges also support Booleans, list Booleans, so you can subtract one range for another or look for intersections between ranges. And in practice, when you're dealing with large lists of entities coming back from a large mesh, using ranges is quite an efficient way of doing that. So I talked a little bit about tags. MOAB supports 2 different types of tags in terms of the storage. One is something we refer to as a sparse tag. A sparse tag is stored as entity handle value tuples, and a dense tag is stored as value for a range of entity handles. So dense tags, in particular, if you have a fine-grained tag like a vertex-based temperature, that's something you would want to store on a dense tag, because they'd store all the values in contiguous memory, and those tend to be highly memory efficient. And MOAB also even supports giving the application back an actual pointer to the native storage in MOAB for tags like that. So you can operate on that the way you normally would on an array of double precision numbers, for instance. Okay, in terms of the mechanics of working with MOAB as a library, I've already said it's implemented in C++. Data is accessed through this MOAB instance. Multiple instances can exist in a given executable, but each instance is not thread safe. We'll be working on that soon because of the direction that all the large machines are going in. In parallel, these instances are independent of each other, except regarding these interprocessor relationships between entities. MOAB supports a variety of platforms, notably not Windows, but we might be working on that soon, depending on if anybody really wants it badly enough and is willing to help us support it. The MOAB configure build process uses either AutoConf or CMake. We maintain both. You don't really have to worry about that because it's built on the machines at ALCF for you. Although I have to say that when you're first learning to use a mesh library in particular, oftentimes it helps to have a local copy of it. So if you're working on a laptop and you have a compile environment there, it's well worth downloading and building the library for yourself because then you can use a debugger interactively, and it works just about the same as it does in parallel. So that's how I do most of my initial parallel development. It builds by itself with no dependencies, but if you're handling real mesh files, and for some of the examples that I'm talking about during this course, you want NetCDF and HDF5. But those are fairly common libraries that you need for other things as well. And there's a web link there if you want to go find out how to grab the library and build it. On a modern laptop, it's a couple-minute exercise if you want to do that at the front end of the... Here's the part of the talk where I go to the code and show you a few things. Okay, so HelloMOAB is just basically a really simple application that instantiates the library, pulls in a mesh, and gives you a little tiny bit of information about it. So apologies to the people who don't speak C++. I'll get to information about non-C++ a little bit later. So basically, you instantiate the interface by just calling a new function. You tell MOAB to load a mesh from that file, and then you can call interface functions to get entities by type. And type, remember, is vertex or edge or try or a number of different types. This source is all doxygenized, and so you can also use this page as a reference to click around in the documentation to find out what the particular classes are about. But this example just basically goes and reads a default mesh file, gets how many vertices, edges, faces, and 3D elements there are, and then just reports those. A couple of the things to note, this range object is the kind of thing to use in this case because you're getting all the vertices or all the elements in a mesh. So we also support a standard vector STL container for these functions. But the STL container for 1 million vertices will have 1 million vertex handles in it, and a range will be about 80 bytes of vertex handles because it just stores start and end. These ranges obey more or less an STL type syntax for working with them. So they define a size function. You can get iterator functions for them, and so on. So if you're used to working with STL containers, the ranges work just about like that as well. Okay, so that's HelloMOAB. Next is this GetEntities example. This does a little bit more in terms of working with the mesh. So again, you instantiate the interface, load the mesh by just telling it the file. GetEntities by handle will just basically get all the entities in the mesh. A lot of these GetEntities functions have a first parameter on the front, and that's an entity set handle that you pass in, and it'll give you information about the entities in that entity set. And so we use a special handle of 0 to denote the whole mesh. And that kind of function allows us to not have a whole separate set of functions for interacting with an entity set. So when you want to interact with an entity set, you just give it the handle of the entity set, where if you specify that handle as 0, that means the whole mesh. When you're getting the entities for the mesh, is that something that you typically cache, or is it relatively efficient to ask for that again? And it's sort of in between. It's fairly efficient to get all the entities in the mesh in the form of a range. But if you're going to use it several times in a single function, those range objects, or even if you want to cache them in your application, those range objects, especially when you're dealing with large lists of entities, are fairly memory cheap. And so it's not that big a deal to cache them either, Although if you're doing mesh changes later on, you can get stale lists and all that. So for this example, we get all the entities in the mesh, then we loop over the entities, and again, range defines iterators and begin and end functions, so it looks a lot like STL. You can take a handle and get the type from that handle. Now, since our handles are simply bit masks, these entity type from handle is actually just simply a bit mask operation inside MOAB. You can even implement that on your side of the interface and make it really efficient. So it depends on kind of how sensitive you are to memory efficiency or time efficiency. In this example, if it's a vertex, we get the adjacent entities, in this case by dimension, so we get the adjacent three-dimensional entities, and we report what those adjacencies are. A range defines a print function for printing the contents of the range. I'm not sure if we define a stream operator, but I was looking at that earlier and think, why don't we do that with the stream? So we should do that with the stream. For non-vertices and non-entity sets, this example will get the connectivity and report that, where a non-vertex entity is defined by which vertices it uses. And so this example shows you how to grab so that's it, really basic example of getting a mesh out of a file, telling you what's in it, and then getting a little bit more information about each of those entities. Okay, so that's HelloMesh. Told you all that stuff. One thing I didn't mention when I had the code up, MOAB has a CN class, and CN stands for canonical numbering. When you're dealing with unstructured mesh, there's always this question about, well, what are the vertices that define a tetrahedron, and how are they ordered? And in tetrahedra, it's fairly easy because they're always right-handed around a base face and they point up towards the apex vertex. But when you're talking about a hex element and the numbering of the edges, do you do the bottom edges first and then the top edges and then the middle edges, or do you do the bottom edges and the top edges and the middle edges? And those ordering sort of questions vary from code to code. So the canonical numbering class has both definitions of the canonical numbering that's used by MOAB and functions for querying it. So you can say, here's face number 5 of a hexahedron, which vertices define this face. I've seen 6 different codes implement 7 different versions of functionality like this. So that's something that I want to plug just in case you implemented your own version of it yet. What usually happens is somebody implements a triangle because they need a triangle, and a tetrahedron because they need a tetrahedron. And somebody 3 years later asks them, well, I want to do a quadrilateral. Can you do that? And oh no, I forgot to implement the quadrilateral in my numbering, and everything has to go back. And so using a system like this gives you all that numbering from the start and a way to query it. Another thing that you tend to run into with real applications is what I call aentities, or intermediate dimensional entities. So for a 2D mesh, sometimes you need the intermediate edges or the interior edges, and sometimes you don't. For a 3D mesh, sometimes you need interior edges and faces, other times you don't. Real meshes usually come with only the entities that they need for defining things like boundary conditions. So if you have a pressure boundary condition on one side of your mesh, you'll get faces for that side, but not all the interior faces. So in MOAB, you can request the creation of entities by requesting them from adjacency calls. So you can ask, okay, here's a hex, what are all my adjacent faces? And there's an additional parameter in that function call for MOAB that says creative missing, and if it's true, it'll create all the faces and give them back to you, even if they hadn't existed before. And so that provides a way to get that information explicitly if you need it. But by default, MOAB does not create all those entities explicitly. Sometimes it matters, like for tet meshes, representing all the interior faces and edges, depending on how you represent those, can increase the memory storage cost by a factor of 4 to 6. Whether that matters to you or not depends on how many other variables are associated with your mesh entities, but sometimes it matters. To force creating of interior edges or faces for the whole mesh with MOAB, I usually get all the vertices using GetEntities by dimension, use the range version because that'll be really light memory-wise, and then just call getAdjacencies with that creative missing parameter of true, and that'll create all the faces in your mesh, and then you won't have to worry about it after that. Once entities are explicitly created, when you say get all the entities of dimension 2 or get all the adjacent entities of dimension 2 with creative missing of false, it'll only give you back the entities that are explicitly represented. Also, there's another thing that GetAdjacencies does that can be quite useful. When you're dealing with unstructured mesh, you're often doing things like, okay, here's a vertex, give me the adjacent faces. But also oftentimes you're saying, okay, here's an edge, or here are two vertices. I want to get the faces that share these two vertices. So I want to get the adjacent faces. So you can do Booleans on the return list that come from adjacency functions with MOAB. So in this example, if you called GetAdjacencies passing in vertices 1 to 4, you want faces back, and you pass an operation of intersect. That means your result will pass you back just quad 1. Whereas if you pass a parameter of union instead of intersect, and you pass vertices 1 to 4 in this example, you'll get back quads 1 and 2. So it depends on the application what they want back from that API call. But this provides a way of cutting out a few lines in the application code to filter down your list. In this example, if you say, give me the adjacencies from vertex 3, give me the faces, and give me the union, that'll give you quad 1 and 2. From vertices 3 to 4, give me faces, give me the intersection, and your list comes in with quad 2 and quad 3, and you're asking for vertices 3 and 4 adjacencies, it'll just pass you back quad 2. So that's the intersection of the results of the adjacency call, quads 1 and 2, with the list that went in, quads 2 and 3, and that's the intersection. So in that case, it just saves you a little bit of code, allows you to do a little bit more filtering straight from the API call. And sometimes, if you pass in a large range, sometimes doing the filtering down in MOAB can be fairly efficient, whereas it might not be as efficient if you do it in the user code. Okay, so a little bit more information about sets and tags. The combination of sets and tags is one of the most powerful abstractions that I think are in MOAB. I have yet to see a kind of simulation data that I cannot represent with sets and tags in MOAB. It's proven incredibly useful and versatile. I've already said that tags are useful as both fine-grained and coarse-grained data. Sets can have parent and child sets, and this is different from contains relations, and that's useful for representing things like graphs of sets. Let's see, some more about sets. The whole mesh is specified through the API as handle 0. MOAB has two types of sets. The easiest way to explain this is one is like a standard vector, where it's in the order that you put them in, and a single thing in that vector can be stored multiple times. And the other is like a standard set, where it has some internal ordering, and a given thing can only be stored in there once. And they're each useful for different things. So by default, MOAB doesn't keep track of which entities are in which sets. So if you put entities in sets, and then you go back later and delete that entity, that set membership is going to be stale. And the reason MOAB doesn't do that is because it tends to focus on memory efficiency first. And hanging a set inclusion list on every entity can get fairly expensive for large meshes. There is a parameter that you can set when you're creating entity sets in MOAB. It's called the tracking flag that says keep track of what entities in sets. And you can set that for individual sets. And what that does is basically handles set membership as an adjacency. So vertices can be adjacent to the entities that use them, like a vertex can be adjacent to the quads that include them. It can also be adjacent to a set that includes that vertex, so that when you go and delete the vertex, it'll go and remove it from that set. So again, in some cases that's useful, and in other cases that's a waste of memory, so it depends on the application. Sets are a fairly abstract concept, but not rocket science abstract. The MOAB API itself does not bind specific set purposes. So if you look in the API for MOAB, you won't see anything about a Neumann set boundary condition, because that's just a collection of mesh faces or edges that have a particular purpose, but it can be represented as an entity set, and so you just store it as an entity set. On the other hand, MOAB does define conventions for conventional uses of sets. So there are a couple of header files in MOAB tag conventions and parallel conventions that define various tag names, and the comments in those files describe what they're used for. So specifically, MOAB defines a material set, Dirichlet set, Neumann set, name, parallel partition, several other tags that are used to mark sets used for that purpose. So when you read in a mesh from a finite element storage format like Exodus 2, and look for the entity sets in the model, you might get back some entity sets that are marked as being material sets. And those are the equivalent of material designations that come from the file. So depending on the mesh file format that you're reading from, in some cases when you read a mesh, you can even get back the original geometric model topology. So for a CAD file, you can read in and get the volume that was resolved by these mesh elements and the CAD surfaces bounding these volumes and so on. Okay, so my next example is SetsNTags. It's again, a fairly straightforward example that shows basically how to go into a mesh, get the sets that are defined in the mesh, and look for tags of specific types. So again, you read the file. Further up, I define a couple of different tag names that I want to specially look for. Each tag is defined by a handle again, and each tag has a name that refers to that tag, and each tag can be given a value for different things in the database, like for each set or for each entity. So in practice, the way you query this stuff is you get the tag handle, and then you look for entities that have that tag on it, and MOAB provides functions to do that. And so this example basically goes and looks for material sets and Dirichlet sets and Neumann sets. So it gets the tag for each of those, looks for entities defined with that tag, and then prints out some information about those entities. I'm running out of time, so I'll have to speed it up a little bit. Recall in a parallel mesh, you have this notion of sharing entities between processors. And MOAB uses the parallel com class for querying information about entities. And recall there's this degree of parallelness that I talked about before. There's this degree of parallelness that I talked about before where you can either load the entire mesh on every processor, or you can just load the mesh, or you can resolve entities on the interface, or you can exchange ghost elements also. You can control that in two ways in MOAB. You can tell MOAB when you load the file, here's all the things that I want to do when you load that file, up through and including exchanging ghost entities between processors. Or you can load the mesh first and then tell it to resolve shared entities and then tell it to exchange ghost entities between processors. I tend to recommend that you do it all at read time because then you don't need to worry about it afterwards, but in some cases, you may not want to do that. I'm going to leave you to look at the example of doing that on your own. The only difference between HelloMOAB and Hello Parallel MOAB is the fact that you pass an option string to the load file command that has substrings delimited by semicolons that tell it, okay, I want you to resolve shared entities and I want you to exchange ghost cells. And that's it. If you call that from a parallel operation, from a parallel running MOAB, that load file is a collective operation. It does that, all those tasks and the returns, and then you have a parallel mesh. And the Hello Parallel MOAB also tells you how to go and query, okay, find me all the shared vertices between processors and tell me about the ghost entities and things like that. These are the standard things you're going to be asking a mesh library for when you're working with a parallel mesh. And so that's fairly common to need that sort of thing. Okay, so there are some data plots about parallel I/O and MOAB that I won't go over. You can look over on your own in a Hello Parallel MOAB. Putting it together, I tried to think of an example that was relatively easy to understand, but still demonstrated working with a parallel mesh. And the thing I came up with was something called Lloyd relaxation. So in serial, it's a fairly easy algorithm to understand. You have an unstructured mesh. For each element, so in this case 2D faces, you take the average of all the vertex positions, and that goes into a tag. That's the centroid of the face. You do that for all the faces. And then you go over all the vertices, and you average the centroids of all the faces that use that vertex. And on the boundary, you have vertices that are fixed in space. And so basically, that's a smoothing algorithm. Makes the mesh more smooth across it, makes the size transition more gradual as you go across the mesh. So you can start with a mesh like this. You do a few iterations of Lloyd relaxation, and you end up with a mesh that looks like this. In parallel, that algorithm looks like this. First of all, you start with a mesh that has ghost faces. So the solid lines here are the pieces of mesh that a given processor owns, and the dotted lines are ones that it doesn't own. And this layer of ghost elements is important in this case for avoiding a round of communication between neighbors. So in the parallel algorithm, again, and I indicate shared but non-owned vertices with an open red dot. So in this algorithm, again, for all the local faces, you compute a centroid by averaging the vertex positions. You do that for the ghost faces as well on a given processor. After you do that, for the owned vertices, you compute a new vertex position by averaging the position of all the faces that use that vertex. And then after doing that, and in this figure, this processor computes a new position only for this vertex. And on the adjacent processor, I've indicated that new position with an open blue box. And similarly here, there's a vertex that's owned by this processor that computes a new vertex position here. So after that's done, so these two steps are fully parallel, embarrassingly parallel. They don't need any information from adjacent processors. After you do that, you call an exchange tags function, and what that does is communicate the owned vertex positions to all the processors that are using that vertex. So basically, you compute face centroids, then vertex positions, and then exchange owned vertex positions with any processor using that. And then you turn the crank and do more iterations like that. And so what it looks like with the real mesh, you can start with a mesh like this. I should have drawn the partition on there, but I didn't. And you end up with a mesh that looks like that. So it's a smoothing algorithm. But again, it shows the kinds of things to do to communicate data between processors. And all the communication functions in MOAB through this parallel comm class are phrased in terms of sets and tags. So for instance, you just say exchange tags. You can give it the tag that you want to exchange. You can give it a set of shared entities. If you don't give any, then it'll exchange the tag for all shared entities that have that tag. So think of it as a higher level way of writing mesh-based code, where the mesh library takes care of some of the details of passing the messages, especially in the case where you're sharing mesh with 60 other processors instead of just one other processor. MOAB has an interface for accessing from C++ or C. If you're interested in accessing from Fortran, we've defined a common interface called the iMesh interface as a collaboration with a number of institutions. And we defined a common C-based interface that's also directly callable from Fortran. The data model used in the iMesh interface is almost identical to the one used in MOAB. And so you can call the same sorts of functions to get the same sorts of information from the library. And if you're using MOAB, you'll get the same information back going through the iMesh interface as you will going through MOAB's native interface. They just may look a little different because the data structures are slightly different. There's also, I've referred to before, we have a geometry interface called iGeom and a relations interface called Lasso. These are my implementations, CGM for geometry and Lasso for IREL. And I have 1 minute left, so I'll do this really quickly. And that allows you to recover relations between mesh and geometry so that you can, for instance, refine a face that's on a curved CAD surface and project that new vertex down to the CAD surface. There are a number of tools packaged with MOAB. Those are executables that are built with it. So typically the first thing I do when I look at a new mesh, I'll just run MB size on it, which tells me how many entities are in the mesh, and different options control how much it tells you about what's in there. Working with parallel mesh, oftentimes you need to partition it. So MB part in the MB Zoltan tool subdirectory is the utility that we include to partition meshes. It uses the Zoltan and Metis libraries that you can get elsewhere. You have compiled versions on the Vesta machine that you can use if you want to generate larger partitions. That's the only one that's really critical in this class. There are some advanced topics that I don't have time to talk about. Like I said, MOAB can give you direct access to tag storage. In some cases, that really helps in terms of efficiency. MOAB provides tools for mesh searching, both serial and parallel, based on tree decompositions of the mesh. Something we've worked on extensively in MOAB is solution transfer, where we want to transfer a field from one mesh to another in parallel. And that can be tricky because you can't control decompositions. And it's an unstructured mesh, so you're not sure that that pieces of the first mesh are on the same processors as pieces of the second mesh. There's some information in your slides about CGM, which is the geometry library, and Lasso, which is this relations tool. And finally, to summarize, mesh tends to be involved in most parts of the simulation process. So in practice, you're touching mesh or you will be when you're working with real applications. In terms of student-y things, mesh-related things tend to be an ideal mix between math and CS and engineering or applications. And so if you feel torn between those three places, maybe working on mesh-type stuff is the thing for you. MOAB and Friends are easy to use and powerful tools for working with mesh-related data, but that's my opinion, and you're welcome to form your own in the exercises. So I've told you just about nothing about kind of researchy topics that happen in the field of meshing, but there are a lot of researchy topics that get studied. Probably the best place to get a survey of that is to go to the International Meshing Roundtable series of conferences. All their papers are online, and we really get a wide variety of different kinds of research going on. And again, you'll see people from math and from CS and from engineering departments, so there's a pretty wide variety of work going on. A recent book just came out on Delaunay mesh generation, and these guys are some of the top guys in the field and are really, really rigorous. And so if you want a look at a good meshing book, look there. Herbert Edelsbrunner is a topologist, but he's written a fairly small 100-page book on geometry and topology for mesh generation. That's really a good intro to some of the CSE type things we deal with in meshing. And then here are a few pointers to some of the work that I do. And finally, there are just a boatload of jobs and research topics in this area. So if it interests you, there's all sorts of interesting work to do. Thanks. So there are two parts of that question. So the previous question was, can we handle higher order meshes? This question is, how do we handle boundary layers in meshes? And that's a question, there are two parts of the answer. The first is how you generate them, and the second part is how you store them, or how you represent them and query them. So techniques for generating boundary layers, I think Mark will probably touch on later, Mark Shepard, tomorrow. So I'll leave that for him. How you represent them, I'm kind of a nut about these entity sets, if you couldn't figure that out from what I said. So in my opinion, you should be representing these with entity sets down in your mesh and marking the entity sets with some sort of tag that says this is a boundary layer. And I personally have not developed any conventions for representing boundary layers like that, but I am fairly close to doing that because we're just generating a new boundary layer generation tool in some of my other work. But basically the question is, how do you access it as data that you're getting from the library, because oftentimes you want to know something about it. Mark, you had a comment.
We exactly use mesh sets for controlling boundary layers so that if you keep them in boundary layers, they don't get screwed up
All right, terrific. So Mark represents them that way too. And oftentimes you have 6 different libraries and they represent boundary layers with 7 or 8 different methods. It helps if you have a convention for representing those things so that the codes know what to look for. And that's the kind of thing that we're trying to do with this common interface development, common data model development.